Hey guys, this is Spiral Review for Spiral 19. First off, we're going to start off with graphing and variation problems. And I'm going to look at my rational function first. So we've got to identify a few different characteristics, the horizontal asymptote, vertical asymptote, x-intercept, and y-intercept. I'm going to start off with my horizontal asymptote just because it's listed first here. And to do that, I'm going to compare these two guys since we have the same degree in the top and bottom. And in this case, in doing that, we end up with just 3 as a value. So y equals 3 would be my horizontal asymptote. Next up, for my vertical asymptote, I'm going to take a look at values that can't exist here. And in doing that, we get x minus 5 is equal to 0. So x can equal 5 for that. 2, 3, 4, 5. We get my vertical asymptote. For the x-intercept, the general rule of thumb is anything that makes 0 show up over here. And to do that, we're really looking at what would cause the numerator to be 0. So in this case, 3x plus 7 is equal to 0. And in solving that, I get x is equal to negative 7 over 3. And negative 7 over 3 is a little bit bigger than negative 2, so it's going to be down here. Okay, and that's a y-intercept, not an x-intercept, so I'm going to erase what I just did, if it'll let me, and draw this more appropriately on my x-axis. Finally, for the y-intercept, we're going to do 0 in for x, and we get 0 plus 7 over 0 minus 5. 7 over negative 5 is going to be negative 7/5, which is a little bit less than 1. That gives a pretty clear picture of what the graph looks like on my left side. And the right side, because this is a basic graph, is just going to be the opposite of that. For our second problem, we're talking about the level of Miss Giaquinta's anger, and it's jointly related to the number of students. Okay, let's call that, I don't know, I don't like using S, maybe X, who refuse to do their homework, and the number of missing chairs. Missing chairs we could call Y, and if there were 3 missing chairs, I guess the anger is the third one. Let's call that A. So I could say that the anger is equal to some kind of joint variation. That's going to be some kind of a constant. And we've got an x and a y. So when I plug things in, we're looking at A is, I get a value for this. 3 missing chairs, so that's y. X would be 10 students refusing to do their homework. K and anger is at a 10. We get K is equal to 1 over 3. Alright, we're going to go back in and take a look at the anger. If there were 10 missing chairs, so that's Y, 4 students refusing to do the homework, and K is 1/3, and we get A is 40 divided by 3. Next up, we got some simplifying rational expressions, in other words, factoring, and lots of factoring. My first guy, we've got 3x squared minus 29x plus 56. Who makes this problem? So I'm looking for things that multiply to 168. I can't write a 6. There we go. X squared and add up to negative 29. Well, the only thing that I know that multiplies to 168, I want to say it's 12 times 14. I think that's right. And then I'm going to build stuff from there. So that means that we could be looking at 6 times... if I divide this one by 2, I got to multiply that by 2, so that's 28. That doesn't add up to 29. That could also have been 4 and 42. Also doesn't go to 29. 2 and 84, even worse. 3 and 56. Nope. We did 4, 5 doesn't work. 6, 7 will work. 7 times 24, because that's divided by 2 times 2. Nope. 8. So that's 4 times 2 is 8, so divide that by 2, 21. And wow, we finally got ones that worked. So that's 3x squared minus 8x minus 21x plus 56 over, and the bottom's going to factor into x plus 7, x minus 7. It's nice when that works out. So we're going to have x and 3x minus 8, and then minus 7 and 3x minus 8, x plus 7, x minus 7, x minus 7, 3x minus 8, and then we've got x plus 7, x minus 7, and finally we can begin to look at the domain. So x equals 7 and negative 7 cannot exist. Then I can do some reducing, and I can see those guys cross out, and I'm left with 3x minus 8 over x plus 7 with domain limitation x cannot equal 7 or negative 7. Woof! Next one. Oh, joyous day, even more factoring. Well, the first one is going to factor into 2x and x. I think it's going to be x minus 5 and 2x plus 3. On the bottom, that would turn into 4 times the quantity x plus 8. And I'm going to keep the dividing part here for a minute. The top is going to factor into 4x plus 3, and no, it's not. 2x plus 3 and 2x plus 3. Oof, almost messed that one up. And the bottom, the easiest factoring so far, is x plus 7 and x plus 8. Okay, we do domain round 1. Anything that is denominator cannot be 0, so x cannot equal negative 8 and negative 7. From that, and we already had negative 8. Next, I'm going to do some flipping. 2x plus 3 and x minus 5 over quantity x plus 8 times 4 multiplied by x plus 7, x plus 8, and that's over 2x plus 3 and 2x plus 3. I'm going to keep my domain from before. X cannot equal negative 8 and negative 7. And to that, I'm going to add x cannot equal negative 3 over 2, because when I flip that, I add some new difficulties to the domain. I'm going to do my reducing at this point. So we got 2x plus 3s, we got an x plus 8, and I'm left with x minus 5 and x plus 7 over 4 and 2x plus 3. And the domain restriction on that, x cannot equal negative 8, negative 7, and negative 3 over 2. Next up, we got to solve some rational equations. And to do so, I'm going to find some common denominators. We've got something equal to 0. Let me write that as 0 over 1, just to be annoying. And then on the right side, we're going to have 4 over x minus 5, x plus 5, and x over x minus 5, nothing to factor. Next up, domain. My domain is x cannot equal 5 or negative 5. Okay, next up, common denominators. X minus 5's first. Those two are all set. Here we've got x minus 5 and x minus 5. We're going to see that part doesn't actually matter in a minute because the 0 cancels everything out. And then finally I'm going to have to add x plus 5. If I do that on the bottom, so must it be on the top. And x plus 5 on the left. And again, we're going to see in a minute that that doesn't actually matter. So we get 0 over x plus 5, x minus 5 equals 4 over x plus 5 and x minus 5 plus x squared plus 5x over x plus 5, x minus 5. And at this point, we can multiply the whole thing by x plus 5, x minus 5 to clear the denominators, and you're left with 0 is equal to 4 plus x squared plus 5x. And by golly, that looks factorable. I'm going to rewrite that as x squared plus 5x plus 4, and that factors into x plus 1 and x plus 4. Both of which are going to end up in the domain, which is fine. So we get negative 1 and negative 4. Good practice is plugging that back in to make sure that those actually still work. All right, number 6, which I wish were our last problem, but it's not. We're doing the same thing. 2 over 1. 3 over x and negative 1 over x squared. I'm going to make them all be the same denominator, and it might be nice to write x squared as x times x. We need 2 x's at the beginning. We need an additional x in the middle, and at the end we already got both, so we're okay. So 2x squared over x squared plus 3x over x squared is equal to negative 1 over x squared. In other words, by the way, domain x cannot be 0. 2x squared plus 3x is equal to negative 1. Bring that over. 2x squared plus 3x plus 1 is equal to 0. By golly, that looks factorable. Let's turn to 2x plus 1 and x plus 1. In other words, x equals negative 1/2. X equals negative 1. Next up, we've got sequences and series. For number 7, we're going to write a general rule for the sequence below, and then find the 8th term. It might be helpful to figure out what's going on here. So it looks like between the first and the second we're adding 0.5 and then we're adding 0.75. Oh man, that's not actually, so it's going by adding. What if I check by multiplying? So 1 to 1.5, well that's like multiplying by 1.5. And then 1.5 to 2.25 is multiplying by another 1.5. Oh, this is a multiplying rule. So my general or explicit rule would be my first term, 1, multiplied by whatever I'm multiplying each time, in this case 1.5, to the n minus 1. To find the 8th term, we're going to plug in 8. 1 times 1.5, 8 minus 1 is 7. So that's going to be 3 over 2 to the 7th power, which I'm not going to figure out. So A8 would be 3 over 2 to the 7th. Next two terms of the sequence below, okay, we have to figure out what's going on. 2 to 8, well, that's either plus 6 or times 4. Then 8 to 32, that's either plus a bunch or times 4. This is a times 4 and times 4 rule. So the next two terms of the sequence, 32 times 4 would be 128. 128 times 4 would be 256, 512. This is another geometric rule. So we're looking at the rule for the nth term is going to be starting number 2. Ratio is 4 to the n minus 1. Next section, we got to find the sum of some series, and we're given some sigma notation for this, so it might be nice to figure out exactly what's going on here. So it's saying we want the sum of the first 1 to 3 terms, so the first 3 terms, using the rule of 3n minus 2. So in other words, for n equals 1, 3 times 1 is 3 plus 2 is 5. For n equals 2, 3 times 2 is 6, plus 2 is 8. And for n equals 3, 3 times 3 is 9, plus 2 is 11. And all I'm doing is adding these 3 pieces up. 5 plus 8 is 13, plus 11 is 24. For 9b, we're doing the same thing, but with a different sequence to use in our series. Now we're doing the first 5 terms, going from 1 to 5. So first term, 3 times 1 squared is 3, minus 7 is negative 4. Second term, 3 times 2 squared is going to be 12, minus 7 is 5. Third term, 3 times 3 squared is going to be 27, minus 7 is going to be 20. Fourth term, 3 times 4 squared is 48, minus 7 is 41. And fifth term, 3 times 5 squared, that's going to be 75, minus 7 is going to be 68. Okay. Negative 4 plus 5 is positive 1, plus 20 is 21, plus 41 is 62, plus 68 is 70, 130. For number 10, we're looking at the sum of the series, and we're looking at the first 8 terms. This is geometric. So I'm going to start with n equals 1, and n, so 1 minus 1 is 0. Half to the 0 is 1. Term 1 is going to be 4. Term 2, 2 minus 1 is 1. 4 times a half is 2. Term 3, 4 times a half squared is going to be 1. Hey, I noticed that as I write these out, each time my terms are getting cut down in half. I wonder if I could use that instead of actually calculating all of these. So we get 1 times a half is a half, and then a fourth, so it's fourth, fifth, and then an eighth would be sixth term, and a 16th would be a 7th term, and then a 1/32 would be an 8th term. So we've got to add all these things up. This is going to be best in terms of 30 seconds, but I'm going to go off on the fact that you, at this point in your mathematical careers, know how to add fractions and not finish that part of the problem. Oh man, then it looks like we got the same thing as what we just did, but now instead of the first 8 terms, we're looking at an infinite series. So what happens if we keep moving the series forward? And for this we have a formula, which we know that the sum of the infinite series for a geometric series, first we got to check the r value is less than 1, so we're good there. So this is going to converge to a number. It's going to end up approaching a number, and we end up with my first term divided by 1 minus that common ratio. In other words, 4 over 1 minus a half, which is 4 over a half, which is 8. So 8 would be the sum of this entire series.